Not a big crowd. Okay, well, anyway, welcome to this morning's, um, God, it's funny, I forgot that I have two roles here. This morning's workshop on stochastic, batch methods and RL and all. We've got a great lineup today, uh, um, and I should get going. So our first speaker on the program is Anna Busic, but her and her baby girl are both quite not well. I just got some reassurance that things seem to be stable, but she's not able to speak today. So I'm giving the lecture she would have given, which is some really new results on what we call Zap Stochastic Approximation. And I'll talk about implications to Q-learning. So in terms of partners in crime, we've got Shuang Chen, who really pushed all this forward and did a lot of hard work. And then Aditya, who is the daddy of Zap, and will be giving a talk after me. And Fan Lu, who's great help with simulations and all, is just a new graduate student. And of course, Anna Busic, who is the speaker today. And then crime is over here. So basically the very origins of some of the new results in this paper came out at a coffee shop near this place near Inria, where Anna Busic works. And yeah, she's a research scientist at Inria in Paris, in an awesome position there, and in computer science at ENS on the other side of the river in Paris. And I'd be introducing her right now, and I'd say I had a Google Research Award, and she's done amazing work in simulation methods and matching models. And we've also done a lot of work I'm excited about, including work in reinforcement learning. So, but also many thanks to the Simons Institute. When Aditya and I got to visit in 2018, it was absolutely, and also Anna Busic was there. It was absolutely incredible for all of our careers. And of course, thanks to our sponsors as well, NSF and Aero. And also note this, next July, there'll be a textbook based on a lot of what I'm talking about today and the boot camp in September. Okay, so I'm going to give another crash course in stochastic approximation. Some of these slides are from the boot camp. That's where the mistake was, Aditya, from my boot camp, with a typo corrected from the boot camp. A return to Zap. Many of people have seen this before, but the story is a lot clearer now. And some really wonderful new results on stability and all that. And then just end with some simulation studies, and that'll be it. And I'll ask the moderator to tell me when 5 minutes are up. Okay, what is stochastic approximation? So again, I think many people have already defined this. Martin Wainwright mentioned this. It's about root finding. We have a function which is defined as an expectation. And we would like to solve this using some simple scheme. And the way it's done is you first think about an ODE and first verify, and this is what I would call the ODE method, is first make sure that ODE is well behaved. So what that means is that the solutions to this ODE converge to a fixed point, and that means that this f bar of theta t would converge to 0 as desired. This is the real goal, because that's what we're trying to solve. Once you have verified that, then you can go through and you could do an Euler approximation. That'd be pretty silly because it would be so complex. So instead, you do this noisy Euler approximation. So you replace the expectation with these random measurements. And sometimes W is phi, I just realized. So W and phi are the same thing. Later on, it'll become a phi. And this works, okay? I mean, convergence of stochastic approximation requires very little information, little assumptions at all. It's very much like the law of large numbers. So basically, it's saying that Euler approximations are robust, and that's it. So so rates of convergence is hard, convergence is not so hard. All right, so that's what stochastic approximation is. Yeah, and again, that's the message. That Euler approximations are robust to measurement error. That's all that's ever done in these proofs of convergence. All right, we're finding proofs that Euler schemes converge. All right. So the best reference is Vivek Borkar's monograph. I mean, of course, there are other great books. The Venice Tutal is fantastic, and Kushner and Yin is encyclopedic. Vivek's going to have a new edition soon. It'll be even better. So again, so here's the procedure of design. So again, I've already said step one is to make sure that you get convergence. And again, you're going to have to modify dynamics. That's the entire point of today's lecture. And also, details as well is talking about modifying dynamics or changing the problem so you get a better ODE. Then there's an issue of gain selection. So, you know, in Q-learning, in like the original papers, and in all the theory of stochastic approximation, at least historically, it's often a typical choice has been just G over N. And that is justified because of the fact that you get the optimal rate of convergence. The mean square error converges like 1 over N. Under an assumption that we have this Hurwitz assumption for the linearization matrix at the equilibrium theta star. So you go and linearize that matrix. You make sure that this matrix is Hurwitz, which means you make sure the gain G is large enough, and then you get this 1 over N rate of convergence under conditions. You know, I mean, not the noise and so forth. And it requires some muscle in general. And then you can actually identify the constants because this matrix here satisfies the Lyapunov equation. So you actually know the constants. And there's a center limit theorem and all of that as well. All right, so there's an issue of gain selection. Now, I'm not saying you have to use G over N. In the end, for the kinds of algorithms I'm going to be talking about, we will have to use G over N. I'll explain what I mean as we go. All right, so there are two sources of error that I really want everyone to understand before you go home. One is the variance I just talked about. You know, I'm going to, when we talk about ODE approximation, we have to make a change of time scales. So we solve this ODE, but then we evaluate the time at this new time scale where we sum the step size alpha k. You know, this alpha k is what appears here. So one is the fact that that's, you know, sigma could be large. So that's what I mean by number one. There's variance, okay? There's variance. And there's a missing thing there. It's, yeah, and sigma goes to 0, but it could be big. I mean, yeah. In the previous notation, there's a 1 over N there. The other thing is that we've done a really good design. So our ODE is fantastic. It converges very, very quickly, but we've got this awful scaling, which destroys everything. We're slowing down time through this, because of this change of variables, you know, and that could destroy everything. So this tau n can be going very, very slowly. And moreover, in the nonlinear case, that case of nonlinear dynamics, we could really have trouble with gain selection. And I'll give some examples to explain why. Okay, but we see in RL applications that if you take, even with like a favorite choice, where you take G over N plus 1 to the rho, where rho is less than 1, or less than equal to 1, if you're far from the equilibrium, you might have to crank up the gain. You might need a really large G. And then you're exploding the noise, by the way, you know, and so you've got some problems there. But once you get closer, then we have a theory for what the optimal G is, and it might be much, much smaller and have a completely different conclusion. And I'll give an example to try to make this clear in this talk. All right, and so here's an example. So this example is mainly about the second point. So it's completely contrived example just to you know, just to show this interesting phenomenon. So basically, we're doing stochastic gradient descent. We have a loss function, which is an expectation. And you see here that my phi turned into a W, or a W turned into a phi. And I chose it so it's quasi-convex, but not convex. So its gradient, here you have F bar is minus the gradient. It's a squiggly thing that was just cooked up for fun, all right? But it's quasi-convex, so gradient descent will work if we could just do pure gradient descent. All right, now what I'm pointing out here is that the asymptotic theory of stochastic approximation would concentrate locally on the equilibrium. Here we have theta star equals 0. And the fact that the slope is -1 in a large scale, you know, would expect something very, very different if we're looking at a very large initial condition. And, you know, so locally you converge like e to the -4t because the slope here is -4, but globally it's slower. It's like e to the -t. You know, roughly speaking. You know, to get a crisp bound is hard. So it turns out that if you want a crisp bound, the only thing I know how to do is get this is basically, this was known as a sector nonlinearity, and the lower sector is given right there, and that is a slope of about -1/3, okay, -0.34. And that turns out to give you a bound on this rate. And once you have a bound on the rate of convergence for the ODE, then you get this very, very sad story right there, where we get, if we don't make G big, we're going to get this crawling along convergence rate for just a deterministic thing. So nothing stochastic, just we've transformed the ODE, so it sucks. It's thrown everything away. Okay, so we need G, say, bigger than 2 maybe to kill this deterministic behavior, but locally G star equals 1/4 is fantastic. Now this is a really boring example because the difference between 2 and 1/4 isn't really that big. I could have fiddled around with this and made it as big as I wanted. I could have made this 200 by making this more flat. You know, it's just you know, it was my first thought. Okay, but the main thing is this. Here, after 1 million iterations, if you use this 1/n step size with the optimal gain, you won't get anywhere. That's like 3 seconds. You know, take a look. The stochastic, because it's a large initial condition, 100, you can't see the volatility very well. The stochastic process and the deterministic process are following each other really well, but it stops after less than 3 seconds, even though n is 1 million. You don't get anywhere. Well, if I crank up the gain by putting this row here, so I've got, remember there's a row somewhere. If I make row less than 1, say 0.9, then I get further. I get all the way up to time about 5 seconds. And if I make it 0.8, I get all the way to about 11 seconds. And there, by then, I've been near the equilibrium for a long time for the ODE and also the stochastic guy. All right, so I can hear a lot of you who are experts in stochastic approximation saying, you're an idiot. Sean, you all know that you don't do this. You do Rupert-Polyak averaging, as Martin Wainwright talked about. And yes, solves the problem. So just go through and, oh yeah, well, forget it. There was a comment here. If you start off with theta 0 equals 0, you do get a CLT kicking in like that. If you start off with theta 0 equals 100, it doesn't. But about Rupert-Polyak averaging, it solves the problem. Okay, for this problem, what I do is I run one of these algorithms with a row less than 1, average the last 2/3, say 80% of the run, and what you get is perfect optimal variance, and that's it. Problem solved. So that's it. Crank up the gain, average the remaining 50%. Done. For this problem, that's true. All right, and the reason is because cranking up the gain kills off the nonlinear dynamics, and then you reach steady state very quickly. You by the high gain creates lots of volatility. Well, you average it out. And that's what polycomb averaging is. And you see here that the center limit theorem is just fantastic. And it converges very, very rapidly. All right. All right. Does this always work? No. Okay. So here's an example from Q-learning. So basically, it turns out that Martin Wainwright, I guess it was around the same time, I think we did it first, we showed that for Q-learning, you need a gain of 1/1 minus beta to get the right convergence rate. Martin had some really clever analysis in tighter bounds. But we had this, back in a few years ago. And if you use that gain, it works pretty well. You get volatility, and after 1 million samples, this is for the standard type of Q-learning, there's still a bunch of volatility, but your Bellman error is reasonable. Now, if you use the Aditya gain, which you're going to learn about in the next lecture, it's just stuck forever and doesn't do a thing. All right. So Rupert Polyak to the rescue. We'll crank up the gain and average. Well, that's what happens. So here's an experiment with rho equals 0.85, which is high gain. And that's, instead of 1/n, it's 1/n to the 0.85 and 1 million samples. And we see it doesn't work. It just fails. Completely fails. Now you could fiddle with this and eventually make it work. You could probably fool around and crank up the gain and do some averaging. It's not plug and play though. It's just not plug and play. Now, well, for this particular problem, you're going to see that Aditya is going to have a solution that's different than one that I'm going to talk about. But the problem here is when we're looking at higher dimensions, you've got these awful condition numbers. Rupert Polyak averaging might require an really big gain, huge increase in volatility of your estimates, and that takes a long time to average things out. And here, we probably could have used a larger gain, but then we would have needed larger averaging. All right. So Rupert Polyak is not just like something you can abandon, you can throw in anything. And Martin actually had another example that made that point as well. Okay, so what I want to talk about is this return to Zap Q-learning where you can solve everything at once. And the main message here is that there's new theory that really is awesome. So basically, just again, the challenges we faced in this OD designed for Q-learning, all of us, the whole RL community has faced, is stability. We don't know how to design the dynamics of the algorithm stable, and we don't even know if this solves a relevant problem. You can say projected Bellman error and make yourself feel really happy, but what does it mean? It really, there are conditions where it means something, like if the true Q function is in your function class, but I don't expect that to hold very often. So that's a big challenge. And then also there's this condition number issue. We have this 1/1 minus beta, where beta is the discount factor. And that causes all sorts of numerical problems, which have been talked about in almost every lecture for the past few days. We've seen a 1/1 minus beta in half the lectures in the last days. Wouldn't it be nice if we could linearize? Get a linear system. We want this to go to 0. Why not a first order linear system? F dot equals minus F. Why not do it? So that's it. So basically, this is now we're calling this, and friends in Georgia Tech are calling this the Newton-Raphson flow. Vivek pointed out this was introduced by Smail in 1976. Vivek knows everything. And so, we've got what we want, if we do this. And that's what Zap Q-learning, Zap Stochastic Approximation is. So Zap Stochastic Approximation just means the stochastic approximation translation of this ODE. And you all know the chain rule. So you know that this turns into an OD for theta because you can apply the chain rule on the left-hand side. All right. And so basically the trajectory is the solution just moves in a straight line, towards 0. That's what this is saying. Okay. All right. So I'm just going to say a few words about convergence and all of that, and how to get an algorithm. So this is an algorithm. Basically, you introduce a matrix gain, because the Newton-Raphson flow, after you perform the chain rule, has a matrix gain in it. It has this minus A of theta T inverse, where A is this linearization matrix that comes up in the variance analysis. So we have a matrix gain stochastic approximation algorithm, and then we have online estimates of this matrix, which we'd like to have, right? And so we have to have access to the gradients, the derivatives of this function f. Well, we'll have those in a neural network setting, as I'll talk about. Right? Now, the issue is that we want to track A of theta. And so for that reason, the only way that's possible is for this thing to be large. You need high gain, okay? Because we want to do this tracking. All right, so basically, again, for this to be true, we need high gain. So gamma n over alpha n is going to go to infinity. And what we're going to do in this talk is always, always, always take alpha equals 1 over n, because if we don't do that, we're not going to get a reliable approximation with the Newton-Raphson flow. I mean, in the theory, we're going to do that. I mean, in numerical experiments, we will hack around a bit, but for the theory to be crisp and beautiful, we do that. And then what we've done everywhere is to take gamma n to be 1 over n to the rho, where rho is between a half and a 1. So it's the standard 2 times scale setting. All right. So the stability is virtually universal. And subject to assumptions of the noise and so forth, you're getting the optimal variance because in the end, you're using the matrix gain, which is the foundation for the optimal convergence theory pioneered by Rupert and Polyak. So, so you get everything, you know, you get the two challenges are all killed in one shot. You get the optimal convergence rate, the optimal with the optimal covariance, and you completely kill the dynamics. It becomes a linear system when you make a change of variables to look at the f coordinates instead of the theta coordinates. So it's just to me, it's just a beautiful toy. You know? All right, Zap Q learning. So basically, Zap Q learning, we have a root finding problem in standard Q learning. We have a function of theta, which you'll find in all of the many of the talks recently and all the papers, which is given here. You know, this lower bar, whenever you see a lower bar, it just means I'm taking a minimum. This is the standard fixed point equation you're trying to, I mean, root finding problem you're trying to solve in Q learning. And the most standard thing like in DQN is just take the gradient of the Q function to be this this funky thing here. All right, so it's a root finding problem, and there's virtually no theory for stability or anything. And again, this is a hidden theory of DQN. I mean, some of you nodding your head saying, of course, but a lot of you don't know that. This is really what DQN is trying to do, and also most extensions of Watkins' Q learning algorithm. And what makes it difficult is we don't know anything. Does it have a root? We don't know. Is there an inverse? We don't know. And then when we go to Zap, it's discontinuous because A of theta is discontinuous. All right. So, the theory of Zap was incredibly difficult because of the lack of continuity. So that's why this paper is so long on trying to show that we don't even show that the OD approximation holds. We show that any weak limit of the scaled process has enough properties so it mimics the important properties of the Newton-Raphson flow. And it really took mainly Shuang had to learn a lot about generalized derivatives and stuff to make it work. So that's what made it work. But this stuff, these first two things, I mean, these are parts of the problems with Q learning even without Zap. I mean, we don't know about stability or anything. I mean, theta dot equals minus theta. I mean F bar theta. Nobody knows when that's that's stable, except for in the tabular case, or quantizing, binning, things like that. But it's really open. Okay, but anyway, so the paper resolves these things. So the video is sort of fun, or a poster where we talk about these two issues, and we use regularization to deal with if A is not invertible, we just look at a approximate inverse. But this is still open, you know. I mean, we just took it for granted that has a solution. It's amazing; it always seems to have a solution. All right, so let's just let's wrap up. I'm done. I'm just going to show you an example. We, you know, not me, that's for sure. I wish I could do this. We ran this on a bunch of standard examples like mountain car, you know, Acrobat, cart pole, and just took some neural networks. And remember, we're trying to solve a root finding problem. We're not minimizing anything. There's no optimization here. It's a root finding problem. And so we're not doing anything. We need A of theta equals partial theta of F bar of theta. The estimates come from a neural network. You know, so we're not using neural networks. We're not doing gradient descent. And I mean, it might not look like much, but we're getting, you know, great performance, but we're not messing with, it just always works. We have theory to say it always works. And when we run it, we don't have to mess around with metaparameters much. It just, you know, almost always works. If we take a neural network that's too small, we'll sometimes get crappy behavior. But there wasn't that much fiddling around. It's a very, very reliable approach. And, you know, so that's it. That's all I've got to say. There's some examples. So in conclusion, the start of the talk was about how reinforcement learning is cursed by dimension, variance, and also the nonlinear algorithm dynamics. Second order methods can ensure stability as well as give you great variance bounds. So use them when you can. In terms of future work, a lot of us would like to kill the projected Bellman error and have some better, more approaches to Q learning. And also look at applications of stochastic optimization. We're looking at, you know, acceleration techniques in recent work. And control variance could be an interesting add-on to all of this, as it's been useful in actor-critic methods. Okay, but that's all I have to say. Thank you. And you'll see there's a bunch of references back here. So I think if there's a clarifying question or something very quick, I should go to Q&A. Where is that? Oh, damn, I can't see Q&A. How funny.
There are no questions though.
Oh, there are no questions. Okay.
I mean, I can't say anything on Q&A.
Okay, cool. I think because I'm sharing my screen, it's blocked everything off. So, okay, so what I'm going to do that. So yeah, there'll be a break soon, and we'll have a great discussion then and all. So I'll just introduce our next speaker, and I'll stop sharing.